Let's revisit the third property of inverse, where it was stated that A inverse transpose is equals to A transpose inverse. We'll begin with this expression first. A inverse times A transpose. Now, if this A inverse exists, A inverse A is equals to identity. The identity transpose is equals to identity because identity is nothing but a diagonal entries of ones. We now want to go from this equation to this equation, and we use the property of transpose. Basically, AB transpose is equals to B transpose A transpose. If you compare the terms here, you'll see that the equation agrees. Now, for this equation to be identity, this expression must be the inverse of A transpose. For this is a definition of inverse. A transpose multiplied by A transpose is inverse is equals to identity. Remember, we have to prove the inverse on both sides. A inverse times A is equals to A times A inverse equals to I. So the second equation, you have to prove it the second way around. We shall not do it again. Please revise this by yourself. In this slide, we'll talk about trace of a matrix. A trace of a matrix is the sum of the diagonal entries of A. To have diagonal entries of A, it must be a square matrix. And basically, we're taking the diagonal entries and we're adding it up together. So the expression of a trace is the sum of the first diagonal entry all the way to the last diagonal entry. And in this example, we are doing 15 plus minus 4 plus 6, and the answer is 17. Now, we now talk about the properties of a trace. Given a square matrix A, the trace of A satisfies the following property. The trace of A plus B bracket is the same as trace of A plus the trace of B. The second property, a constant multiplied by A, the trace of this is the same as bringing the constant out, multiplying by the trace of A. The third property, the trace of A multiplied by B is the same as trace of B multiplied by A. So interestingly, even though AB is not equals to BA, as we have discussed previously, in 7.2.1 we had this, AB is not equals to BA, nevertheless its trace is interestingly the same. The last one is obvious. Since an identity matrix has only one along its diagonal and zero otherwise, then the trace of the identity matrix is the sum of this diagonal of ones is the same as the dimension of the identity matrix. We will not go into a theoretical discussions of these trace properties as well as why the trace operator is defined this way. But interestingly, the trace operator, using these four properties, there's only one way we can act on the matrix. That is, the sum of the diagonals is the only operator that satisfies all these four properties. In this next slide, we discussed determinant of a matrix. What is a determinant used for? The most common application of the determinant in Our course should be the use of determinant to determine if the matrix is invertible or not invertible. When the determinant is not equals to 0, the matrix is invertible, and when the determinant equals to 0, the matrix is not invertible. The determinant is only applied on the square matrix. Another interpretation of the determinant is by 3 blue 1 brown, and in here the link is provided. You can take a look at the determinant, in which he described that the determinant actually determines the factor of change, that means the volume of change in the length or the area of an operator on a vector. The larger the determinant, the bigger the vector will be changed by the matrix A. For our case of 2 by 2, this is the famous formula for the determinant of A. It is nothing but taking the diagonal entries A11 times A22 minus A12 times A21 for a 2 by 2 matrix. You should remember this by heart. The determinant of A has various notations. It can be written as determinant bracket A, or sometimes we use the absolute sign and put A inside, where A is a matrix. Both these symbols are used commonly to describe the determinant. Some properties of determinant, we have seen this before. When determinant of the matrix A is 0, the matrix is singular. It means that it has dependent rows and columns. The determinant of A times B is the same as the determinant of A multiplied by the determinant of B. The determinant of the inverse of A is same as 1 over determinant of A, and hence that is why when the determinant of A is 0, meaning it's singular, 1 over 0 is infinity. And lastly, determinant of A transpose is the same as determinant of A. We shall not prove these properties. We'll just use some of these when required. For a more comprehensive treatment of determinant, I suggest Strang 1806 lecture in 2011, The Properties of Determinant. This concludes our review of Unitary Matrix Operation 7.2.2.